Hi, this is series on topology, and today next few lectures will be on product spaces, product topology. My plan is to start with the product of two spaces, but then with the motivation how to define the topology properly and use it to define a topology on arbitrary product of spaces. Okay, I hope all of you will enjoy. As usual, all the preliminary things which are usually never discussed will be discussed in detail, and how to think of them geometrically, intuitively will also be explained. Okay, right. Stay tuned. Let's get started. Yeah, the best reference is a forthcoming book on topology by me and my student. Okay, I'm sorry I forgot to write his name. Right. And but what I'm going to do will also be found on generating topologies, but then it's for the later part of the course. Okay, and also some parts of that is used in functional analysis, a first course, section 7.1, 7.2. But what I'm going to do today is something very simple. Okay, let's get started. So suppose I have two topological spaces x and y. If you want to think of them, x tau x, y tau y, two topological spaces. Right? Then let's look at the Cartesian product xy. This is a set of ordered pairs, as all of you know, so that x belongs to x and y belongs to y. This is just a set at present. Right? Notice that there is a natural maps from x cross y to x, which I call pi of x, and the other one pi of y, x cross y to y. Here what is it? Pi of xy. This is a projection onto the first factor. This is a projection onto the second factor. They are called projections. Right? Now something very interesting happens. Let us look at this pi x is a map from x cross y. This is a set to y, a topological space. Sorry, x a topological space, and similarly pi y is from x cross y to y, a topological space. Whereas here on the domain is just a set. So what I can ask for, we ask for a topology tau on the set x cross y, which makes pi x and pi y continuous. See, this is not the way it is usually taught, but you will enjoy this. Okay, this is a very beautiful way. You should learn this. Okay, so what does this mean? Which makes continuous? That means pi x is as a map from x cross y to tau from to x tau x. This must be continuous, and similarly this must be continuous. So I want to look for a topology tau. But this question is very easy. It's actually a stupid question. Why? Okay, take tau to be discrete topology. Okay, so that's not a good answer. See that? Why it's not a good answer? It has nothing to do with your map pi x, your map pi y. Okay, if I put discrete topology on x cross y, then any function from x cross y to any topological space will be continuous. Okay, there is no bearing on the given data, namely the maps pi x and pi y. You understand that? So how do I refine this question? So we refine this question. How do I ask? I ask for a smallest topology on x cross y. Smallest topology, let us write tau cross x cross y. Okay, so that this maps pi x from x cross y to, let me write tau equal to so that I do not keep writing to x tau x and pi x cross y tau 2 y tau y are continuous. So we are asking for the keyword is now the smallest topology. Okay. Now you may wonder, does such a thing exist? Right? Yes. What is the answer? Because remember, there exists already discrete topology. Okay, on x cross y, which makes this continuous. Therefore, if T is the collection of all topologies tau, topology on x cross y, okay, so that pi x from x cross y to tau 2 x, and similarly pi y x cross y tau 2 y, these are continuous. So this set is non-empty because the discrete topology belong to that. And we know intersection of topologies, this is again a topology on x cross y. Okay, and it's easy that this will be the smallest topology. Okay, making pi x pi y continuous. Okay, its a topology is clear, and why it's the smallest? If okay, it makes tau pi x and pi y continuous. Why? That's very again clear, because you give me any u in tau x, then pi x inverse of u. This pi x inverse of u belong to each and every tau. It belong to tau for every tau in t. Right? Therefore, pi x inverse tau belong to this. So you call it as tau x cross y. Then this belong to this. This belong to each and every tau. Therefore, it belong to the intersection. Similarly, pi inverse of v, where v is in tau y, okay, that belongs to tau in this family for every tau. Okay, for every tau in the family t. Okay, just think about. Okay, so this topology makes pi x and pi y continuous. It's the smallest, because if tau dash is any topology which makes this continuous, that is going to appear here. Therefore, tau x plus y, sorry, x times y is contained in tau for every tau in capital T. Therefore, it's the smallest topology. So this is a bit too much. Okay, I know, especially if your set theory topologies are vague, you will suffer. But go through this. This insight textbooks refuse to give. Teachers refuse to give. Pause, review, and then proceed. Okay. So, existence of such a topology is proved. Topology tau on x cross y is proved. Okay, because it's intersection of all such topologies in the capital T. Okay, we have seen that. Now what we want is a description. Okay, if you had been following my lectures on topology, you would know that given any subset A of P of x, then we have shown that there is a smallest topology which contains tau of A, smallest topology tau A which contains A. Okay, we proved its existence, then we gave a concrete description. Okay, please learn that. If you have not watched that video, please go ahead and watch it. We are going to use it again here. So I want a description of this product. This topology is called the product topology. Okay, now how do I describe? Okay, now start with the thing. Suppose I have u in tau of x, right? Then since pi x from x cross y tau to x tau x is continuous, therefore pi x inverse of u must be in tau. Similarly, for every v in tau of y, pi x inverse of v must be in tau. Do you understand that? So, is that clear? Therefore, I have a collection A. What is the collection A? The collection A is set of all elements of this type pi x of inverse of u and pi y inverse of v, where okay, u is in tau x, and maybe you write this, and union v in tau y. Okay, that is A is going to be pi x inverse of u is in tau x, and union pi y inverse of v is in tau y. Okay, so this script A must be contained in the topology because they are all open. That means all of them should be in tau, right? Because tau is the topology which makes pi x and pi y continuous. Therefore, since these are all open in tau x, therefore their inverse image should be open in tau. You follow that? Yeah. So any topology tau which makes pi x pi y continuous must contain A, and this is the smallest topology. That means, okay, my topology tau is nothing other than the smallest topology, that is smallest topology which contains A. All sets are the form, pi x inverse of u, where u is in tau x, and pi y inverse of v as v is in tau y. Okay, pause, review, proceed. Alright, now we shall again explain that. But before going, let us try to understand this object. Okay, suppose, okay, let us, before we proceed further, let us look at some pictures. Suppose this is x, this is y. See, this is how you usually think of. Don't think of them as line. X is one space and y is another space. You are taking the Cartesian product. Alright. Now, suppose I have an open set U. Okay. Then this is my U. Then what is pi x inverse of U? Let us recall this is set of all x comma y in x cross y, so that pi x of xy must be in U, but that is same as x must be in U, right? And here there is no condition on y. Right? Therefore, it's going to be like this. So this is nothing other than u cross y. So this is your pi x inverse of u. Do you understand? Now let's look at now what is pi y inverse of v. So I start with the v here. This is my v, right? Then go through that. Pi y inverse of v will be set of all xy and x cross y, so that pi y of xy, which is y, must be in v. Therefore, there is no condition on x. Therefore, x would be anything, but y has to be in v. That gives me this picture. Okay. So this object is nothing other than x cross v. That is your pi y inverse of v. Okay. Make sure you understand this. Right. Now again, just go through this. We had already seen, but I am just okay. Please go through the video which talks about the topology tau A. I am unfortunate, I don't remember the thing. Topology generated by, or the smallest topology containing A. Okay, please watch that video. As far as possible, I try to do in somewhat self-contained manner, but you should do that. Now remember, now pi x inverse of u and pi y inverse of b both are in tau. This is a topology. Therefore, I know pi x inverse of u intersection pi inverse of b must be in tau, because this is an open set in tau, this is also an open set tau in tau. So what does that mean? So again go through this. So this is your thing. I hope I did this. Yeah. So the common thing is going to be this. That is your pi x inverse of u intersection pi inverse of b. Yeah, is that clear? Right. Now if you, so we are going to define a topology. This is exactly defined using this A, but I will pretend that we do not know. Therefore the topology tau I am going to define is set of all w in x cross y, right? So that for every xy in w there exists ux and tau x, vy and tau y, so that xy belong to pi x inverse of ux intersection pi y inverse of vy. Don't be intimidated. This is not what you would have seen in product topology, but bear with me for a while. This insight will help you. Is that clear? But what we know what this is? This is ux cross y and intersection. Sorry, and this is contained in w. And this is x cross vy. Okay, what is this object? When does xy belong to this? So when does a point, let's say pq, when does it belong to that? It belong to this means p must be in ux and q must be in y, but it also belong to this, that means p must be in x. That's a redundant condition because p is already in ux and q must be in vy. Therefore this object is nothing other than ux cross vy. Right? Are you following? Pause, review, proceed. So with the topology tau I can rewrite this set of all w in x cross y, so that for every xy in w there exists u in tau x and v in tau y, so that xy belong to u cross v and that is contained in w. In other words, if I call this as this, u cross v, u is in tau x and v is in tau y, this is a basis for product topology. Because what does this mean? This means sets of the form u cross v form a basis, right? Because w is going to be union of u cross v. Yeah, I hope all of you remember basis, etc. Okay, it's unfortunate. Okay, unless you learn those things well, you will suffer. Okay, please go back to my videos on basis, etc. You will understand. Okay, so what have we done now? Let us summarize. The product topology on x cross y is the smallest topology on x cross y, which makes pi x and pi y continuous. That's the first point. Therefore, what we found out, that means all sets of the form pi x inverse of u, pi inverse of b must be in this topology, right? Okay, therefore as a basis what we saw, the basis for topology is u cross b, where u is in tau x and v is in tau y. These are the things we have found. Do all of you agree with that? Okay. Okay. Now that I have made this thing clear, let us go through a very small thing. Okay, this is called product topology. Again, let me recall. So when a W in x cross y is open in product topology, if for every xy in W, I should be able to find u in tau x, v in tau y, so that xy belong to u cross v. That means x belong to u and y belong to v, and this should be contained in W. Again, look at the picture. Again, it will be good to have a picture. So I have x cross y, and when do I say something this is open, this is my W, give me any point, then I can find an open set here and open set here. So this is u cross v, and this is your point x comma y. Right? So do you recall in R2 with respect to the max metric, okay, that is distance between x1 y1 x2 y2 is maximum of mod x1 minus x2 mod y1 minus y2. Okay, the open balls are of this kind, right? Yes, you should always relate. You should not simply assume this and you should go ahead. Okay, you have seen such a thing, similar thing earlier. Okay, so is the product topology clear? Now make sure that now with respect to the topology, my pi x is continuous. Why? Because pi x is what? X cross y to x. Is this continuous? Start with u. Then what is pi x inverse of u? It is of the form u cross y. We already know. But that belongs to tau. Why? Because u cross y is already of the form u cross b, where u is in tau x, y is in tau y. Therefore, this is actually a basis element. You understand that? Therefore, pi x is continuous. Okay. Is that clear? So, to make sure that we understand how to work with that, let us prove a very small lemma. Okay. If x and y are Hausdorff, then x cross y with the product topology. Whenever I say x cross y, it will be with product topology. Okay, so how do I prove that? Right? So how do I prove that? We want to understand this. See, like usual in metric spaces and or in a topology, when I have a very good basis and almost all the concepts, it will be easier to deal with basis. I don't want to work with open sets. Remember that trick. Okay, in a metric space also I will work with open balls. Right? In analysis we'll say epsilon delta, but for topology is open ball. Right? Okay. So now how do I find this? So I give a point, let us say xy and a point AB. They are in x cross y, and suppose they are not the same, they are distinct. That means what? Either x is not equal to a or y is not equal to b. One of them must happen. So let us assume x is not equal to a. Right? Then what is that I have to do? I have to find an open set W1 which contains xy and W2 which contains AB, so that W1 intersection W2 should be empty. Right? How will I do that? Let us again look at the picture. So I have x, okay. What I have done now is I have 2 points. This is my point A and this is my point x. They are in X, right? So I know they are distinct, right? That's our assumption. So we are assuming X is not equal to A. Now what do you think I can do? Now X is Hausdorff, right? This space is X and this space is Y. This is Hausdorff. Therefore what I can do? I can find an open set U1 which contains A and U2 which contains X such that U1 intersection U2 is empty. Okay, is that clear? Now I am sure immediately you know what your W1 and W2 should be. Can somebody say what will be your choice of W1 and W2? You can do better than that. Now let's look at this set. And this is your U2 cross Y and this is your U1 cross Y. Okay, right? So there's nothing other than my W1 is Wi is going to be pi x inverse of Ui. You understand that? That is Ui cross Y. Is that clear? W1 intersection W2 is empty. Why it's empty? Because if you give me point any kind u comma v in this, that means u must be in, okay, u comma v is in W1. That means what? If and only if, let's look at W1 is what? Pi x inverse of Ui. Okay, this u comma v belong to W1. If and only if, by definition this is equal to pi x inverse of U1. This happens if and only if pi 1 of uv, namely u, belong to U1, right? For the same reason, when u comma v belong to W2, that will mean if and only v belong to U2. But what is our assumption? U1 intersection U2 is empty. There is a contradiction. The picture already showed. You understand that? These two fellows are disjoint. Okay. Now is W1 open? Yes. Because product topology definition is these are all open sets. Or if you don't like it, they are U1 cross Y and U2 cross Y. They are basic open sets. Correct? So what I have done? I have proved the product of two Hausdorff spaces is Hausdorff. So pause, review, proceed. Okay. Now let's do one more lemma. So this is again similar to your R2. Suppose I have sequence xn yn which converges to xy in any one of the metric D1, which is a sum metric due to usual Euclidean metric. D max is the maximum metric just now I introduced. You know that all of you should know that is this converges if and only if xn converges to x and yn converges to y. Do you remember that? We are going to prove such a similar result about product topology. So let x cross y be with the product topology, then a sequence xn yn in x cross y converges to xy if and only if xn converges to x where in x and yn converges to y where in y. Okay, please pay attention. There I simply said because xn x yn are all real numbers, so I will simply say in R, but what it matters is the first coordinate converges to the first coordinate in the first space, second coordinate converges to the second coordinate of the limit in the second space, second factor. Okay, right. Is that statement clear? Okay. So suppose x and y converge to xy. Okay, I want to know whether it shows that xn converges to x in x, and similarly yn converges to y in y. Okay, this is very easy, because just let us recall again. Let me recall the definition. Suppose, when do I say xn converges to x in a space? Give me any open set U containing x, then there is an n natural number, so that for every k greater than or equal to n, my xk lies in U. Right? This is my x, this is my x, this is my U. So if k is greater than or equal to n, all my xk lie here. These are all my xk's. If k is greater than or equal to n. Right? And the second thing you have to say is, if f is a continuous function from x tau x to y tau y continuous, and if xn converges to x in x, then f of xn converges to f of x in y. This also we had already seen, but let me quickly go through the proof. So we give me an open set V containing fx, right? Since f is continuous, let us look at f inverse of V. Call it U. This is open. Where? In x. And does x belong to U? Yes. Because when does x belong to U? If only if x belongs to f inverse V. That happens if only f of x belongs to V. Right? Therefore x belongs to this. Now since xn converges to x, right? Then what do I know? There is an n. So that for all k greater than or equal to n, my xk lies in U. That is same as saying f inverse of V. That is same as saying f of xk lies in V. So what I have shown? So I have shown that there is an n, so that for all k greater than or equal to n, my fxk lies in V, where V is any arbitrary open set which contains fx. Do you understand this? Okay, please pause, review, proceed. If you have not seen this, go through the proof. If you have seen it, don't worry about, go through the proof in your mind quickly. Okay, now let's look at, I know xn yn converge to xy in x cross y. I want to make use of this result. Okay, what do I want to prove? I want to prove xn converge to x. Where? In x. Similarly, other one. What do you think I will do? All of you know that, right? Remember, product topology makes pi x continuous. Therefore, x cross y to x, this is continuous. Therefore, I know pi x of xn yn must converge to pi of xy. But this is xn and this is x. Therefore, xn converges to x in x. Do you understand the proof? Yeah, I am just using that earlier lemma. Okay, let us prove the converse. Converse is again very similar to the way you proved in R2. X and yn converges to xy in R2. Okay, if and only if xn converges to x, yn converges to y. The same kind of proof. So assume that xn converges to x in x and yn converges to y in y. What do I want to prove? I want to prove x and yn converge to xy in x cross y. Right? So to prove x and yn converge to xy, what is that I have to start with? I have to start with an open set containing xy. Therefore, start with any open set containing xy. Right? But what do I know? I know that there exists an open set U and V, U in tau x, V in tau y, so that x belongs to U, y belongs to y, right? You understand that? So what I am going to show is, I want to show there exists an n, so that for all k greater than or equal to n, my xk, yk lie in U cross V, and hence it lies in W, and hence it lies in W. Is that clear? Now how do I prove that? I am sure all of you know that. How do I prove that? Now I know xn converges to x, right? Now xy belong to U cross V, that means x belong to U. Yeah? And since xn converges to x, U is an open set containing x, therefore I know there is n1 such that for all k greater than or equal to n1, my xk lies in U. Similarly, there is an n2 such that for all k greater than or equal to n2, my yk lies in V. So now all of you know the standard trick. Take n1, n2 and their maximum. Then if k is greater than or equal to n, what happens? My xk lies in U and yk also lies in V. Therefore, the ordered pair xk yk lies in U cross V. So I proved it. Yeah? Is it clear? So we proved the result whatever we wanted. Now let's prove the third result. This is an important thing which I will call it as a theorem. Okay. The theorem says, okay, suppose I have a topological space Z. If you want tau Z, okay, I will not need that. It's a topological space. Suppose I have a function from Z to x cross y. Okay, I want to know when f is continuous. Just stop for a minute. I already talked about sequence x and y and R2 converging to xy in R2 if and only xn converges to x, yn converges to y. Now I want to talk about the function z from x cross y when it is continuous. Are you reminded of some result you have seen in real analysis somewhere? Perhaps analysis of two variables, etc. Calculus of two variables. You must have seen that, right? If f is a function from, let us say something, I don't care what it is, Rn to un R2, R to R2, right? F of x, f of t as f1 of t, f2 of t. Okay, for t in R, this is going to be a vector in R2, therefore I can write the first coordinate as f1 of t, f2 of t, then f is continuous if only if f1 and f2 are continuous. Right? Do you understand? So I want to make such a thing. If this is continuous, therefore take any z, then f of z has to be an element of x cross y. Any element of x cross y is of the form x comma y, right? Therefore this particular x will depend upon z, therefore I will call it f1 of z, and this I will call it f2 of z, right? Therefore I can write as f1, f2. Notice that there is another description. So what is that? F of z, how do I get my x? That's the first coordinate of fz. But how do I get the first coordinate of fz? So I simply compose, right? That will be my x. Similarly, the second coordinate of f will be y. Do you understand that? Yeah. Therefore, my f1 is pi x composite. I wrote pi 1, but anyway it's okay. And f2 is pi y composite f. Do you understand that? Right? Okay. So we want to say f is continuous if and only if f1 from x cross z to x and f2 from z to y are continuous. Is the statement clear? F is continuous if only f1 is continuous, f2 is continuous. But what is f1? The domain is z. For f1 and f2, the domain is z, but the codomain is x and y respectively. You understand that? Okay. Now, if f is continuous, this implies f1 is continuous because f1 is pi of x composite f. Now, f is from z to x cross y is continuous, and this is projection map, and we know the projection maps are continuous, right? In fact, the topology on x cross y, the product topology on x cross y is the smallest topology which makes pi x continuous. Therefore, the composite map is continuous, right? Similarly, f2 is continuous. Okay, make sure you understand this. So now I want to look at the converse. So what is the converse? Assume f1, f2 continuous. I want to prove f to be continuous. right? So what is that I have to show? I have here from Z to x cross y. I want to show this is continuous. What I know is f1 is continuous and f2 are continuous. f1 is from z to x and f2 is from z to y. These are continuous. So to prove continuity, what is that I have to show? Inverse image of any open set, f inverse of w is open, right? But remember, just few minutes before I said that whenever I have a very good basis, okay, any topological notion, I should test against the basis. It will be easier to work with the basis rather than the general open set. So I can as well work, I can assume my W is of the form U cross V, which is a basic open set. Okay, the general case, if you want, I will again prove it. Okay, in case you have not followed. Okay, so I will prove this is open where, right? Now let us look at. So I have a point Z in W, sorry, Z in F inverse of W. That is if only if Fz belongs to U cross V, right? Now what is Fz? Fz is F1 of Z and F2 of Z that belongs to U cross V, right? So this happens when if only if F1 of Z belongs to U and F2 of Z belongs to V, right? What does this mean? This means F1 inverse of U, okay, Z belongs to this and Z belongs to F2 inverse of V. Do you follow this? Yes? Yeah. Now what do I know about F1 inverse of U? See, remember F1 is from Z to X, this is continuous. Similarly, F2 from Z to Y continuous. Therefore, this is open set in Z. And similarly, F2 inverse of V, this is an open set in Z, right? Therefore, F inverse of W is nothing other than F1 inverse of U and F2 inverse of V, because Z belong to, that is Z belong to F inverse of W if and only if Z belong to F inverse of F1 inverse of U and Z belong to F2 inverse of V. That means Z belong to the intersection. Sorry, I wrote common, I'm sorry. Yeah, it's intersection, right? This is open in tau Z, this is open in tau Z, therefore this is open in Z. So we proved this is open. Yeah, pause, review, proceed. Please go through that. See, you ought to learn set theory, functions, inverse images well if you want to survive in topology. Is that clear? Now suppose W is any arbitrary open set. Okay. Now give me any point Z here. Okay, I will prove Z is an interior point of W. Then W will be open, right? Every Z is an interior point. Okay, right? Okay, how do I prove that? Since Z is in W, so I'm sorry, I'm very sorry. What I have to do? Sorry, I have to prove F inverse of W, every Z in F is an interior point. F inverse of W, right? Okay, so how do I prove that? Now remember, that means F of Z belongs to W and W is open where? In X cross Y. That means there is a U and V, okay, so that F of Z, that is namely F1 of Z, F2 of Z, okay, F of Z belongs to U cross V. and that is contained in W, right? F of Z belong to W. W is open, therefore there exists U V, so that F of Z belong to U cross V. Is that okay? Right? Now notice that whatever I did, F inverse of U cross V is F inverse of U, F1 inverse of U intersection F2 inverse of W and V, and that is, yeah, and that is contained in F inverse of W. And this is open in Z, this is open in Z. My point Z belong to this, right? Therefore Z belong to this open set, and that open set is contained in F inverse of W. Therefore Z is an interior point of F inverse of W. So I proved that result. Yeah. So go through that proof. So please learn to think along with me. I am not writing the proof. Once you have got the idea, you can go back and do that. Okay. Again, the picture is the same. Okay. Right. So what you have done is we have defined product topology as the smallest topology on the Cartesian product of the sets x cross y, which makes the projection maps pi x and pi y continuous. Then as a basis we found we have a basis for the product topology, that is of the form U cross V, where U is open in x and V is open on y. Okay, this is all I have to know about product topology of 2. Then what did we show? We proved 3 results. If x and y are Hausdorff, we prove x cross y is Hausdorff with product topology. And if x and y converge to xy in the product topology, if and only if xn converges to x in capital in the space x and yn converges to y in the space y. Last we proved if f is a function from a topological space z to x cross y, then I can write f as component functions f1 f2. Then f is continuous if and only if the component function f1 from z to x and the other component f2 from z to y are continuous. Okay, so this gives some kind of a good idea how to work with product topology. Is it okay? Now there are 2 more results I can do. So if I have 2 metric spaces x and y, right, on x cross y we have a product metric, right? So since with respect to product metric I get a topology on the Cartesian product x cross y. Number 1. Understand the problem, that is more important than the proof. Okay. Now on x I have metric topology tau x, on y I have the metric topology tau y. Therefore on x cross y I have the product topology tau on x cross y, right? On x cross y, therefore I have 2 topologies. What are the 2 topologies? One topology is the metric topology, comes from the product metric. Another topology is product topology got out of the metric topologies on x and y, right? The natural question is, are they same or are they different? What I would like them to be the same, right? We should prove that. And second thing is, that's another thing, very important result. If x and y are compact spaces, then x cross y is again compact with the product topology. So in the next lectures we will attend to these 2 problems. Yeah, stay tuned. If you have difficulty, please go back to my some of the things and again review. Okay, we will meet again. Take care, stay safe.